is about the free vibrations. And free vibration, that means there's no loading. This is our outline. So if there's no sections number here listed, so basically we're going to skip that section. And all the contents here we emphasize is on linear systems. So that means only nonlinear terms like the perpendicular fractions, the kind of things we won't discuss in this class. Right now I'm ready in the final check to upload the second homework. Our second homework will cover the first half. That means from the beginning to here, 2.5. And I'm kind of thinking, because I plan to finish the first half of these sections of these chapters by Friday this week. So I'm kind of planning for the homework due Monday. So I will give it a try. If needed, then I can extend it. But otherwise, we'll be shooting for the end of the day, Monday next week. And then the second set of the homework will be covering the second portions here. So basically, in these chapters, you should have the two sets of homework and get that ready. Over the weekend, I've seen a few people kind of working toward the last minute. And unfortunately, I went to bed about 9, and I woke up at 4 or 5. So if you kind of shoot the email after 9 p.m., usually I don't have time to respond, okay? And I don't think that will be working if you use the last 3 hours, say 3 or 4 hours to push through the application, the submission, get a full score. I don't think that is possible. And in particular, from the homework 2 and 3, you will see the complexity of the doing things will take time. So today I will upload the homework 2, get that ready. And my recommendation is you gradually work into the homework day by day, and don't wait until last few hours. And again, I won't respond to any email after 9 p.m. So don't put hope on any last minutes from me, okay? Simply, I just want to go bed, and then, okay? So we can start the new sections. So here will be introductions of our free vibrations here. And the first one, I want to give you these outlines here, and then we can have the brief introductions. So the free vibrations basically is a system on the vibration of his own initial conditions. So what we call the free is mean the free of external loading. Okay. So if without a system without any external loading, so that means it's going to vibrate on his own initial conditions. Initial conditions including initial displacement and or the initial velocities. Okay, and here is a few examples here. For example, this is a tower, and then here is the simple, a simple approximation to this tower, the top of here. And assuming this whole thing is the bending of the beam, so we have learned, we know how to calculate equivalent spring constant for this cantilever beam. And if we lump approximation using one lump sum, then we can approximate its natural frequencies. And so that means approaching to like this one. And this example is, let me explain. So this is the mass, and this is the spring to approximate this tower. And this one is you see this spring connect to the base, and base is under certain rotation. If you have not taken the NE302, basically this is a cam, design of the cam, and you should know, and defining the profile, basically we're producing appropriate dynamic profile, kind of the acceleration or different velocity to that one. Basically this one is to simulate in terms of the Earth, and simulate the seismic, which means earthquake, okay? So here we're using the cam. Basically, if we take away of this cam, then basically you could imagine the base of this system is under certain excitation. under certain excitation, that excitation is one kind of external loading. External loading applied to the base in return producing relative displacement between the mass and the base, and any relative displacement will cause spring to deform. So basically this topic will be in chapter 3, next chapters, we call it forced vibrations. Okay, so that's one example here. So in these chapters, our focus will be on free vibrations, and that means no external loading. And doing that, I'm going to give you a few quick review. Okay, so here is the introduction of the free vibrations. Okay, and so basically here we're going to have the description of the spring constant, and then taking the free body diagram and forming the equation of motions. So the first step is I'm going to give you a review of the homogeneous equations, because that will be serve as our foundations for solving the equation of motion. So the learning goals for yourself, you're going to set up is these two things. One is you have to know how to apply fundamental dynamics, and apply and drawing appropriate free body diagrams, and from there to formulate the equation of motions. This portion forming in the process of the forming equation of motion, which means taking the free body diagrams, apply Newton's law, or apply other methods that is about the topics of dynamics. Okay, so that means assume you should have the preparation ready. So that means when I go over, and then I'm just direct apply whatever you should know from there. Okay, so any questions about the formulation of dynamics, you should go back to look over your dynamics work, not to me. But of course, quick questions, I can provide the quick hint to you. But suppose I'm not starting from beginning of introducing Hooke's law or under appropriate method. Okay, assuming you should have kind of the prerequisites ready. So this is about the equation of motion. The second one is how to solve the equation of motions, and basically that is going to solve for differential equations. And here I'm going to give a quick review. And so basically, hopefully my purpose is to unify the solution template, and in this way we directly apply to. Okay, so here I'm going to review the tools we can use. And I'm not going to review all the methods you have learned in DeepEQ. Okay, so here I think today 1 hour, lecture hour will be on this one, and then apply to our vibration systems. So we can start from looking at a very general description of the linear ordinary differential equations. Okay, the linear, that means A1, A2, A3, they are linear terms. And actually, in our vibrations, A1, A2, A3 are constant. Okay, so basically here, that is the form we're going to deal with in vibrations. And we consider initial conditions. In general, we assume the initial conditions are non-zero. So based upon this general template, and we're going to see how can we solve for the solutions. And the first step is usually for this kind of the second order differential equations, or even higher order differential equations of this linear form. The solution is in this template. Okay, so we assume the solution is in this form, and A is the amplitude, and P is a certain parameters we can solve for. And then the remaining simply is we introduce, if we assume this way, then we introduce x dot equal to, we take the chain rule P times A E P T, and then we take the x double dot equal to P squared A E P T. So together with the assumed forms, we introduce the three terms back into our equation of motions. So in this way, after you introduce those things, you can find is A1 P squared plus A2P plus A3 times A times EPT equal to 0. Okay. So here from this case, from the boson side, we simply divide this one. So from here you obtain is A1P squared plus A2P plus A3 equal to 0. And this one, you can see P is our, the form here, okay? So the P is the parameter there. So usually we call this, is called the characteristic, C-H-A-R-A-C. We call this as the characteristic equations of the differential equations, or sometimes we call this as the characteristic equations of the dynamic system. Okay, and the root and from here, that is the term we simply can plug in. There's a two roots, P1 and P2, will be equal to, and that is very straightforward. I simply plug in the equations. Minus 2a minus 2a2 plus minus b squared minus 4ac. Okay, so that we're expecting two roots, and usually P1, P2 are called the characteristic roots. Okay, so basically here I try to unify the terminology, so we're going to term and going to communicate. So that is very straightforward, and that is we're going to use this as a template for all of our kind of solution process. And with this one, keep in mind, and right now we're going to discuss three possible solutions, and depends on the content of this. You see, these are numbers, and we're going to calculate within the square root. And square root of, say, real numbers, then that would still be the real number. The square root of non-negative numbers, then that will give us real numbers. If for some reason, if we take the square root of a negative number, which will depend on how the four things they kind of combined coming up. If that square root of a negative number, then basically that will give us the major numbers. So here we're going to have the discussions of the three possibilities. Before we're doing that one, let me move on the slides. So the remaining review is to how to solve for P and A. So basically P is showing there. You simply solve for the characteristic equation for P. And A, we're going to use the examples to demonstrate A basically are relating to the initial conditions. Later, we're going to use examples to do that one. And so relating the ODE to the vibration system, basically here we're going to do the examples and using the free body diagram to form the equation of motion. So that is kind of the outlines here. Okay, so for this page, we have this form, and so we have formed that one here. That is a process there, and usually before we're doing the detail, the solution process. Usually you can assume it's just like we said. You assume the step one is assume the solution is in the exponential form here. Okay. And then the step two is to introduce, just like we did here, and to obtain the equations. Okay, so equation for here is say x double dot a1 plus a2x dot plus a3x equal to 0. So the characteristic equation, let me recite that one here, p squared plus a2p plus a3 equal to 0. Okay, and then solve for p1 and p2. Okay, and later we will detail discussion for p1 and p2. And in the last step, and once you know the p1, the numbers for p1, p2, then the solutions. again, because this is a linear system, so for one number of the characteristic root, we have, say, A1, E, P1T. And we have another form due to the P2, so A2, E times P2T. Because this is a linear system, so that means all the possible solutions will coming from the combination of the two possible bases. Okay? So right now we have this is P2 here. So right now here, leaving to A1, A2, two unknown constant. So the two, A1 and A2 are determined by using the initial conditions. So this is the general steps of solving the equations. And once you have the A1, A2 solved, exactly you know the displacement, basically you solve the problems. Okay? The whole process really depends on the coefficient A1, A2, A3. Okay, so the remaining we're going to deal with is the three possibilities here. So we'll continue back to here. There's the three cases we're going to study. The case one is A2 squared minus 4A1, not A4, sorry, A1, A2, A3. Here is a typo. This one is A3. Okay? So, yes?
Shouldn't that also be just negative A2, not negative 2A2?
Oh, yes.
That's how it was on the slides.
Sorry, that again. Only minus A2. Yeah, thank you. Okay, so that is A3 is greater than 0. Then the second possibility is A2 squared minus 4A1, A3 equal to 0. The third one is A2 squared minus 4A1, A3 less than 0. Okay. So we have such three conditions here, and basically for this case you can see, so here again, here I have a typo, and so basically the right way, let me just get a clean of the writing, that should be this, okay? So you see for the first case, if this number is greater than 0, basically the square root of a positive number will give us the real numbers here. So the whole thing, that means corresponding to is P1 and P2 are both a real number. Okay? Because after they taking the square root, and that means minus A1, minus A2 plus minus a real number, that's still real numbers. So for this case, basically say we have a solution, say minus 1, minus 2, something like this. Okay? And for this case, basically that's saying the P1 equal to P2, and again, they are equal to a certain real numbers. Okay, so for the first two cases we are dealing with is the real number case. The third one, because the numbers within the square root is a negative, so we're expecting the coming up will be a complex number. So that means for this case, P1, P2 are complex conjugate. They are the complex numbers. Okay. So within the three cases, we're going to deal with these things one by one. So that is the case here. And the first case we can look at going over with a slide. So we're going to deal with the case by case. The first one is for this case, and that is showing there, and both P1, the roots are real, and they are different. Okay, so P1, P2 are different, So basically the solution process is equal to this, okay? So again, we solve for P1 and then we take the linear combinations. We must take the complete set. So keep this in mind, okay? So we can take a look at this the two examples and to demonstrate the solution process. For the first equation here, for the first one, you can see the characteristic equation is P squared minus 4P plus 3 equal to 0. Okay, so that is the characteristic. So therefore, from here you factorize, that is P minus 3 and P minus 1 equal to 0. So therefore, P equal to 3 and or P equal to 1. So from here, therefore, we plug into here x over t equal to a1 times e3t plus a2 e t. You good? Okay. And furthermore, if let us exercise and how to find the a1, a2, say for example, and say x initial conditions equal to say 1, and initial velocity say equal to 0. Using the two initial conditions, we can try to exercise how to solve for a1, a2 for this example here. So using this one, basically from these initial conditions, so from here you can see x0 obtained from here you can see x0 simply you plug in t equal to 0, so x0 equal to a1 plus a2, right? So from your obtained form, you simply plug in t equal to 0 to here, so that is a1 plus a2. And from here you can see the given is 1, so basically equal to 1. That is the given information. Okay, and again, we can calculate x dot of t. This one would need a little bit kind of the chain rule calculations. So based upon this, we simply calculate, we take the derivative. So that is 3a1 e3t plus a2 et, right? If you remember exponent of at, take the derivative respective time equal to a times eat. We simply take this formula to here. Okay, so therefore from here you can see x dot 0, you simply again with this calculated term, you introduce t equal to 0, that is 3a1 plus a2. And again, from here you have the given condition that is 0. So basically using the equation 1 and 2, you can solve for a1, a2, right? So with the equation 1 and 2, you can solve for a1, a2. And a2 equal to minus 3a1. And so 1 equal to a1 minus 3a1. So therefore a1 equal to minus 1 over 2. And a2 equal to 3 over 2. Okay, so from here, that is completely solved, these equations. You good? Okay. So we can exercise the second one. For the second one, let me use a different color here. For the second one here, again, the characteristic equation is p squared plus p minus 6 equal to 0. Okay, and then if you do it by plugging into that formula, or you do whatever the factorize, and for example, whatever the p equal to, then we utilize that equation 2a, a1 that is 2, and minus. Okay, so this one is I simply plug into the formula there, so that is 1 minus 1 plus, and that is 5. Okay, so that is minus 1 plus 5 is 4 divided by 2, and then minus 1 minus 2 minus 3. Okay. So for this case, the x of t will be equal to a1 e2t plus a2 e minus 3t. So again, A1, A2 can be solved by initial conditions if you have, if you are given that kind of thing, repeating the process. Good?
How did
Yes.
you get, maybe my algebra is just failing me, but how did you get 5 out of,
I think
Yeah,
it's supposed
one-
to be negative
oh,
6,
negative.
making it a positive. And then
Yeah, sorry, again,
okay, that makes
my,
sense.
yeah. Okay, that is it. I forgot the minus sign here. Yeah. Good. Okay. So that is for the case 1. So using the examples, we kind of demonstrate the first case. Okay, and now I want to proceed to the next page, and will that be okay? Erase this portion. The next portion will be the case Q. Is that ready? Good. Okay, the next case is this one. Assuming the case 2, that means the number in the square root are become 0. So if for that case, and again the form is this, and here I simply pick up the result from your Diff EQ, and again at this moment we simply plug into here, okay? And the form is this because these characteristic roots are repeated. So one term is the constant multiply exponential term. The other is, keep this in mind, constant multiply with t and multiply with the exponent terms. Okay, keep this form in mind. We do the exercise here. So for example, for this example, the characteristic equations basically is p squared plus 6p plus 9 equal to 0. So p will be equal to 2a minus b plus b squared minus 4 times 9. Okay. So from here you can see that is 2 minus 6 and plus minus 0. So basically that have a repeated root minus 3 minus 3. Okay, so therefore the solutions will be equal to C1 e minus 3t plus here I distribute C2t e minus 3t. Okay, so one is simply exponent, exponential form. The other one is you multiply t, a linear function t, with this exponent form. So that is the result we obtained. For this case, it's very straightforward. Okay, so taking the derivative, hopefully you know how to do it. So derivative, basically on the second term here, you need to take the partial derivative and chain rule. So, and very straightforward. Okay. So that is the second case, and using this example, we finish this one. Any questions? Good. Good? Good. And we move on to the third case, and this will need a little bit work. So let me get rid of this one. Yeah, so let me get rid of it. Okay, skip it. The third case is this one. So that means the number within the square root is negative. And so for this case, we know this is plus minus a complex number. So basically, let me re-express these things in terms of alpha and beta for easy to make our writing easier. Okay, So basically, I define this one. Alpha is the real part, and beta is the imaginary part of this complex number. Okay. So for this case, and again, we take a look at here. So right now, the characteristic root is P1, P2 equal to alpha plus minus I beta, the complex numbers. And again, our result still taking this form. Again, we have the E P1T, and we have E P2T. Again, this is a linear system, so we take the superpositions and to superpose the possible solutions together. And again, A1, A2 are determined by initial conditions here. And from this point onward, and because right now P1, P2 are complex numbers, we can do a little bit more work to simplify these expressions, and that means we're leading to certain physical interpretation of the result. And that might not have been introduced to you in the Diff EQ. For that class, I assume that basically the mathematical oriented and have less physical interpretations. But here, combining with our vibrations, we do have something to say. So to do that one, then you do a little bit more steps of the derivations, and stay with me a little bit patient, and then I will explain that to you. Okay. I like to keep these portions, and so kind of let me utilize this space here. So let me expose. So the first term, we simply introduce P1, for example, is alpha plus I beta. Okay. And so again, here we utilize the equations. If you remember, E exponent A plus B can be described using the E times exponent A multiplied with B. We can take up this formula, right? So using this one, basically we can take up is E alpha times E I beta, right? Okay, I simply distribute from exponents to here. And from here, then again, if you remember last time, we introduced a notation for complex numbers. If you remember, that equation is E I theta. Basically, we have is cosine theta plus I sine theta, right? So that is the definitions. I say this is a definition we use quite a bit in complex algebra. So right now, for the second one, I take this. Basically, is E alpha, and then I using that definition to expand the second term. So basically, that is the cosine beta plus I sine beta. Okay? Good? Good. So similarly, E P2T have the same process, E alpha cosine beta my plus I sine beta. So maybe in this one I need to put it is cosine minus beta. Okay, because for the P2 we have P2 is the P2 equal E P2T equal to E alpha minus I beta T. I missed something here. P1 equal to this, and I forgot multiply with T. Sorry, Monday. Okay, so that is the term I missed. Okay, so we simply put into here. So that is T. So that is T here. Sorry about that. Okay, so the same thing, and So in a similar way, this one we have is E alpha t times cosine minus beta t plus I sine minus beta t. Okay, so again, let me further simplify. That is cosine minus beta t is simply a cosine beta t. And sine minus beta t is become a minus sine. Okay. Again, this is the derivation process. So therefore, x of t equal to linear combinations of e p1t plus a2 e p2t. Then if you plug in the e p1t to here, and plus a2 e p2t, and you can do that one similar to me, similar to what I'm doing here, just using whatever the shape, just do it. That will ease your candidate review when you look at your notes. Okay, so you simply plug in here and do arrangements carefully. Actually, the results can be equal to, you can see for the blue term here, we have the base cosine beta t and sine beta t. For the red one, we have cosine beta t, sine beta t. The remaining simply is the sine playing around. So after the linear combinations, and look at this carefully. So this one, again, let me skip off a few steps. And if you like, you can really implement it. Okay. So this one will become e alpha t times c1 cosine beta t plus I times c2 c2 only sine beta t. And I'm doing so right now at this moment for myself without looking at my lecture notes. I don't know in detail of C1, C2, but I know the principle is C1 is a linear combination of alpha t and something. Sorry, the C1 is a linear combination of A1, A2. C2 is a linear combination of A1, A2, and I, the complex number I. Without going to the detail, I don't think that is necessary. But if you like, you can really introduce here. And just 1 or 2 more steps, you get this one. And right now to this one, I don't care what is the C1 and C2. I don't care the contents of C1 and C2. Because either A1, A2, or C1, C2, they still be resolved by using initial conditions. So in the very final step, we're going to do it and by solving the numbers here. So at this moment, I simply want to get the form. Okay, I simply want to get the form. And this is the form. Okay, so that means this is xt. And this form is very, very important. And actually, the success of your learning chapter 2 is on the interpretation, is on the how to say that one, comprehensions of this term here. Okay, so in chapter 2, the majority of our vibrating systems are falling into case 3. Okay, and I'm going to explain to you why. But right now, you keep in mind, case 3 will take a majority of your calculations in vibration here. So this form is very important. And let me explain to you what is the meaning of this form here. Basically, this form saying that, okay, the one is this, we have alpha. This is our characteristic root. We have the real part. And our characteristic root, we have beta, that is our imaginary part. Okay, so the real parts going into here. The imaginary part going into here. Can you stay here for a few minutes? Because that is very important, and I will let you go. Okay, never mind.
Stay here.
Okay. Go.
Question? Question?
Yes.
How does the sign in that final form come into play? Because you're summing that. I see how the imaginary signs cancel out, but I don't know where the sign comes from in the final form.
So basically, C1 is A1 plus A2 something. C2 is A1 minus I times A2 something. I don't care the contents because C1 and C2 going to be solved by the initial.
No, I know that. But so in the blue box and the red box, you're summing those two times the constants, which we don't care about. In the blue box, you have positive sign, imaginary sign, and in the red box, you have minus imaginary sign. But in the final form, and those would cancel out. But in the final form, you have cosine.
I think the quickest way is we simply do it here. So we simply do it is introduce this one. So A1 times this one. Okay. So let me do this one. Alpha t, and then cosine beta t plus I sine beta t, and then plus A2 e alpha t and cosine beta t minus I sine beta t. Right? Okay, we'll simply introduce to here. So right now we have alpha t, so that means alpha t is turned out. Then we're using a different color to highlight it. So here the both terms have this one, so the two terms are take out to here. Okay, and then we're collecting the terms. For this term, that is contributed by this term and that term. So under this case, if you compare C1 equal to A1 plus A2. Good? Okay? And then you compare, right now collecting this term. This term is coming from here and here. So that means C2 equal to A1. The C2 equal to I A1 minus A2 here. Simply is collecting the appropriate terms here. Okay, so in this way you can clearly from this kind of derivation, I think the question is good. So you can tell the contents of C1 and C2 basically as a function of A1, A2. But really don't care because eventually we're going to introduce initial conditions to solve for C1 and C2. Okay, so to this moment, how the A1, A2 relate to C1, C2 is not really critical here. Okay, so right now we come to here, and so that means if we have the complex conjugate characteristic roots, then the real part is go to here, the imaginary part is go to there. So keep this one. Try to get yourself be familiar with these terms, okay? And let us kind of get more understanding of what is the physical meaning of this one. The two terms here, certain constant, the linear combination of cosine beta plus sine beta t. And basically this is a combination of the simple harmonic motion, right? In our homework 1, probably you have an exercise, say cosine 2t plus 3 sine 2t, this kind of thing. So basically this one, once you calculate it, basically this is a simple harmonic motion. It's simple harmonic functions, right? So that is in sinusoidal oscillations. Good? So let me ask you, what is the frequency of such oscillations? Determined by omega. Determined by beta, right? Good? Any questions to this point? Okay. And then what is the magnitude of such an oscillations? The magnitude of such an oscillation is given by this, right?
It would be that times.
Yeah, so this magnitude is decaying. Good? So with this one, two parts. First one is we know this is in sinusoidal oscillations in terms of the frequency which is given by beta. And such an oscillation with a certain magnitude, and that magnitude is decaying over time using the exponential. So with this things in mind, or decaying or exponent. Okay, so with these things in mind, we can take a look at this example, and using the numbers, we can demonstrate the whole calculation process. I'm going to show the result here. Okay, so I want to give myself a little bit more portion. So how about this? Let me get this one out. Okay, so we can do a little bit more exercise using this example here. So starting from beginning, the characteristic equations is 5p squared plus 2p plus 50 equal to 0. Okay, so in this way, p1, 2 will be equal to 2a minus okay, so that we plug into the formula there, and that is minus equal to minus 0.2 plus minus I have some calculation ready, so I simply pick up my numbers here. Okay, so therefore from here you can see xt. Again, let us directly pick up, put into this form, and alpha t, alpha is minus 0.2t. Okay, and multiply with the beta c1 cosine beta t 3.56t plus c2 and sine 3.56t. Okay, and here to know these things, and here let me do a little bit more the acceptations, the derivation here. Again, earlier in your homework, you have an exercise is this. Say C1 cosine beta t plus C2 sine beta t. You know, in this way we can express this into the capital beta t minus v, right? So we have such a form. The x is called the amplitude here. And v is called the phase angle. And again, in homework 1, you have learned and how to determine the magnitude and how to determine the phase angle already. You know the procedures. You're supposed to at this moment. Okay. So with this one, let me do a little bit more explanations here. So this one we can rearrange into this. So basically this bracket and can be put into this form. So the capital E minus 0.2t times cosine and beta 3.56t minus v. And before we fix the numbers, I simply want to give you the numeric examples of demonstrating the important concept. Again, this is this in sinusoidal function in oscillations, and with a frequency 3.56 radian per second. So this is the oscillations. Sinusoidal oscillations at a frequency, the frequency 3.56 radian per second, right? Right now I'm giving to you is the physical explanations, and such oscillations is at a magnitude that is equal to this. So we have oscillations, the two different portions. We have oscillations and we have an amplitude, and we can try to draw it. So the whole things will become like this. So if this is time t, and if this is our xt, okay. And with this one, when t equal to 0, we have the phase angle. So basically, let me just upgrade. Okay, let me do this one. I think I will try is, I'm going to try to define these amplitudes first. This amplitude is, for this particular example, is a decaying. Okay, when t equal to 0 is magnitude equal to capital X, a certain value, we don't know yet, but we know that's when starting from here. And such an amplitude is in exponential decay. So let me just using the dashed line to envelope the applications, okay? And that is symmetric to this one. So this is an amplitude x times e minus 2t. And such an oscillations are confined within such an envelope. So let me draw that one. This one is something like this. Continue. Okay, good. And in precise, and we can define from the peak. Initially, if you remember our definition, this is our phi here, the phase angle. And what is our the oscillation period from peak to peak? From peak to peak, that defines the period. The period of oscillation is equal to 2 pi divided by frequency. The frequency equal to, for this case, will be 2 pi divided by 3.56. And that is seconds. Okay? Is that clear about the physical meaning of these equations? Any questions? No? Okay, so we can have the second stop.